Thank you so much for watching this online video tutorial. Like, comment, and share, as well as subscribe to our channel at Good Better Best Online Videos for more video content. Okay, grade 11s. For tutorial purposes, thank you for watching this tutorial, and hope that it helps you guys answer exam type questions for acids and bases. Acid and base is still part of stoichiometry section, the section stoichiometry. So whatever we see here will be mixed. Unfortunately, there's no, or in this question paper, which is the DBE November 2018 paper, definitely is a mixed question. So there's some stoichiometry questions here, but all built upon an acid and a base reaction. So let's have a look at this question 8. We'll do this together. Okay, so in 8.1 asks us to please explain why a hydroxide ion is regarded as a Lowry-Bronsted base, or as a Lowry-Bronsted base. Now remember, according to their definition, okay, we know what's they have their own definition for an acid and base reaction. Okay, but for question 8.1, let's just write it out here. Question 8, and we'll say the paper name, which is November 2018, and this is also grade 11. Okay, so for 8.1, all right, in the equation there, a hydroxide, or reaction rather, hydroxide ion can act as a proton acceptor. Okay, so if we go here, we see hydroxide. So that's the hydroxide ion over here. Now, a Lowry-Bronsted base means a base is a proton acceptor. So hydroxide here can still accept, all right? It can still accept another proton. Okay, it can accept a proton. Okay. Right, now, as we can see here, just to identify, ammonia is the base and water is our ampholyte. It's acting as an acid here, as it gave a proton to ammonia to become ammonium. Okay, but that's not the question. They say identify the type of bond responsible for the formation of the ammonium ion in the above equation. So that's just 1 mark. Okay, so again, that is knowledge of intermolecular forces and covalent and dative covalent, whatever. So that type of bond, once we go over that section again, is dative covalent. Okay, now as you can see, these questions are all mixed. Okay, so from question 6 downwards, which is the start of stoichiometry, okay, they're all mixed all the way down. Okay, 8.3, write a balanced equation to show how the ampholyte in the above equation will act as a base when it comes with when it reacts with hydrochloric acid. So they're very sneaky here, all right? They haven't told you what the ampholyte is. They haven't asked you to identify the ampholyte. So your brain might not switch to getting to understand or know which is the ampholyte. You would have to obviously identify it like we did in the beginning, okay? Identify what the ampholyte is immediately. All right. So now we've done that. Okay, we need to go and react it, which we know is water is the ampholyte here. We need to go react that with hydrochloric acid and write a balanced equation for it. So I'm going to pick out another color for it though. So we got HCl, okay, in aqueous. Okay, let me just check something quickly. Okay, we got to put the forms in, yes. Aqueous. And let's react that with water, H2O, which is a liquid. Okay, and that's obviously going to give us H3O plus in aqueous solution, which is a hydronium ion, because of course in white, we will not write this in, but just to explain it again, this little positive hydrogen here is going to go over, oh sorry, I don't know why I do that, it's going to go over here to the water, and then we're going to left with just, of course, the chlorine. So let me rock on here, plus Cl minus, also in aqueous solution as well. Okay, so that's our ampholyte, because acts as an acid or as a base. Okay. Cool. So that was acids and bases. Be able to write an imbalance equation. Be able to show that if water reacts with an acid, because this already is your acid, now water is acting now as a base. Ampholyte can act as both base and acid. All right. Cool. Let's rock on now to 8.4, which is a more of a concentration type. This actually looks like it's a definition though. Let's come back and answer the question. 5 decimeters cube of nitric acid, HNO3, with a concentration of 0.75 moles per decimeters cubed is spilled accidentally into a small pond of water. The acid in the water has a total volume of 1,000 decimeters cubed. To neutralize the acid, calcium hydroxide is added to the water. So to neutralize the acid, which is hydrochloric acid, we've added that to the pond, and we get Ca brackets NO3 to aqueous plus water, because now water is obviously disjoined. Okay, or it's been, the acid has been neutralized, so we can obviously, the water still stays H2O and doesn't turn into anything else. Now we've got to use a definition here. Define the term concentration. Okay, so in a normal exam you would obviously be writing that concentration is the amount of solute per liter of solution. Right, amount of solute per liter of solution, or you can write concentration is the number of moles of a substance per decimeters cubed of solution. Okay, but that looks like it's a more of a easier mouthful. So concentration is the amount of solute per liter of solution. Okay. Let me see, do I have enough space for 8.5? I think I do. If I write it a little closer, maybe in another color. 8.5. Since now, based on all the information we got here, we've got a volume of the acid, we've got a concentration of the acid, we've got a volume of the water. No, sorry, we got a volume of the water and acid together. So if we take 1,000 minus 5, we get the volume of the water. And we don't know how much volume of calcium hydroxide was added, or the concentration of it, or anything. We don't know anything about that. Most of everything that we know in this question is of nitric acid, and we know the volume of water. So, sorry, the question used calculate the concentration of acid after it was spilled into the pond. Okay. So first thing we've got to do is find out what is the number of moles of the acid before. So we say C is equal to N over V. So the concentration was 0.75, and the number of moles and the volume was 5. So over here, therefore, the number of moles before it was spilled was 3.75 mole. All right, 3.75 mole. Okay, so now what we want to add is, of course, see now what is the new concentration. So you can make a little heading here or a little section in your answers to say new concentration. Okay, or you just underline it here or something, just to make the marker aware that this is where you're calculating the new concentration. So of course, same formula, C is equal to N over V. And we're going to say, well, C is equal to the number of moles that went into the pond was 3.75. And the volume of the acid plus the water is 1,000. So the 5 decimeters cube of acid going in with the 995 decimeters cube of water. Put that together. And therefore, the volume of the concentration of the acid after it's spilled into the pond is now 3.75 times 10 to the power of negative 3 decimeters cubed. All right, and that's 8.5. Okay, and then the last question, or maybe let's just leave that up for a little bit. 8.6 says use calculations to determine if 120 grams of calcium hydroxide will be sufficient to react completely with all the acid in the pond. So now they tell us, okay, of the calcium hydroxide, they used 120 grams of it. Will it be sufficient to react completely with all the acid in the pond? Okay, so we're just trying to find out if that's the sufficient, if that's the sufficient amount. If it's not, well, this calculation is obviously going to help. All right, cool. So let's, obviously, what we calculated initially, let's just go back to there quickly. C equals N over V, 0.75 of the HCl, N over 5, therefore the number of moles of HCl was equal to 3.75 mole. Okay, now let's have a look at the ratio. Okay, the ratio of HNO3 to calcium hydroxide. Okay, the ratio is 2:1. If we go back to that equation, see, 2, and there's a 1 in front there. Okay, so the ratio is 2:1. So therefore, the number of moles of CaOH2, which is calcium hydroxide, is going to equal this divided by 2 times 1, which is 1.875 mole. So now we've got the number of moles of the calcium hydroxide. And that's pretty basic. Okay. So now what we're going to do is we're going to take this and we're going to equate it into our mole formula. So let's come and use a different color. So N is equal to M over big M. Number of moles is 1.875, and that's equal to the mass, okay, divided by the molar mass of calcium hydroxide. The reason why we're doing this, let me just explain this. What we're aiming to do here is that we are aiming to check if 120 grams is enough, and the way we check if 120 grams is enough is by finding out the number of grams that we actually would need to neutralize it. Alright? We actually need to find out the number of grams that we would need according to theory with this amount of moles. Okay, so let me just get a periodic table quickly. Right, the molar mass is 74 after calculating it off the periodic table, which is 40 plus 16 plus 1, which is 17 times 2. So that's 74. We rock on here, obviously, we multiply both sides by 74 to cancel them out. 74 here times 1.75. And if we just do that quickly, so 74 times 1.875 gives us, for the mass that we actually need, to equal 138.75 grams, which is clearly 138.75 grams is larger than 120. All right, it's larger than 120, which they said use calculations to determine. So maybe they didn't use 120, maybe they just wanted to check. All right, so if that would be enough, so they performed a calculation and they got us to perform a calculation, and we see that no, it's actually not enough. So our conclusion is therefore no, 120 grams is not sufficient. And that ends off question 8 of the 2018 November paper. There is another method to 8.6, and I'm going to just demonstrate it quickly. So we were told to check if 120 grams would be sufficient, so we can actually go ahead and check that. First of all, let's find out how many moles of calcium hydroxide would we have if we used 120 grams of it. So let's take 120 grams, which is the mass, divided by the molar mass, which is 74, and we get the amount of moles to be 1.62 mole. Okay? Now, we obviously know the number of moles of HNO3, right, to equal 3.75 mole. Okay, we calculated that already. Okay, so that's how much moles of CaOH that we have, okay, and this is of HNO3. So now we again have to use the ratio here, and of HNO3 to Ca brackets OH2. All right, we see that, okay, and that is 2:1. Okay, so that's still 2:1 from the reaction that we see here. We still see that. Okay, now all we got to do is do the same thing with we did in the previous question. We would have seen that we got to take half of 3,75 divided, of course, by 2, multiplied by 1, and then we'll get obviously what x will be equal to. So that equals obviously x here in this case. Therefore, the amount of moles of CaOH2 would still equal 1,875 mole. Exactly the same way we did in the previous question. Okay. So now we can see that that's the amount of moles that we should have, or that we would need with the mole ratio. This is how much we have with 120 grams. So we can clearly see that, first of all, the amount of moles that we need is greater than the amount of moles that we will have with 120 grams. So therefore, the same conclusion. No, it is not sufficient. It's not sufficient, or we can use one word for in space of 2. It is insufficient. All right. No, it is insufficient. And that's the other method for doing the same question, question 8.6. Alright, this is question 8, guys, for a new question for the 2017. We're going to work backwards in here. Okay. We're going to go all the way down to 2015. So if we can't finish 2015 in this tutorial, we'll go all the way for the next one. But they say 2 reactions of sulfuric acid are shown in the diagram below. Sulfuric acid reacts with sodium hydroxide, and then we get a salt plus a byproduct called product Y. And then in reaction 2, it reacts with water, and we get an ampholyte A plus hydronium, which is H3O plus. Okay, now ampholyte, of course, it can react as an acid or a base. All right. So let's define the Lowry-Bronsted base definition. Okay, and they only want for the base, not the acid base. So we have to just go out of this quickly to a new layer. We have to obviously obey the question. Okay, so again, also question 8, but this is 2017, grade 11, paper 1. Paper 2, sorry. And it's November. So 8.1.1, the Lowry-Bronsted definition of a base is a proton acceptor. Okay. And 8.1.2, so let's go into the next one. It says write down a balanced equation for reaction 1. Okay, so that's not that difficult. Okay, so we can start out with what we know. H2SO4, the aqueous solution, plus NaOH in aqueous solution. Sorry, there we go. Nice little straight arrow. And this is just a normal reaction, so it's a salt, and so that's going to be this part I think is going to bond this. That's going to be Na2SO4 and plus water. Okay, and water looks like water is actually the byproduct Y here. All right, and sodium sulfate here is the salt. So I just got to balance the equations. So I'll use another color for the balancing. So there's a 2, no, sorry, not a 2 there. There's a 2 here to balance the sodiums out here. And then we got 2, 4 hydrogens, and here we already got 2, so we put a 2 in front of there, and there we go. Our equation is balanced. We just write this in aqueous solution, and this one is a liquid, water. 8.1.3, write down the name of the salt that's represented by X. Okay, I said it already, so we just write it down now. Sodium sulfate. So that's sodium sulfate. Okay, and then I think 8.1.4 is write down the formula of ampholyte A. Okay, so that's a new reaction now. 8.1.4. So let's just react H2SO4 that reacts now with water to get a certain, well, let's actually just fix that, to get a certain product plus H3O plus. Okay, so water is definitely acting here as the liquid here. Now this is in aqueous solution, so they don't ask for this, but obviously I'm just showing you how it's going to be formed. This is definitely the acid that must be the base, because we already have identified the acid, so one must be the other. So one hydrogen proton here is going to go over here to form the H3O plus, and if that is the case, then we've got HSO4 minus. So this over here is our answer of ampholyte A. Okay, this is ampholyte A. Ampholyte A. Right here. Okay, HSO4, and you can see that this can probably further react with water to form more hydronium, and just a sulfate will remain. Okay, and the last one for 8.1 though, before we get to 8.2, write down the formula of the two conjugate acid-base pairs in reaction 2. Okay, so you will have, of course, these two pairs here, the conjugate acid pairs. So for 8.1.5, from the above reaction, you will have HSO4 minus and H2SO4. Just change it out there. H2SO4. So this would obviously be the conjugate base of an acid, of the acid. Okay, and then you'd have the base and the conjugate acid of a base, which is H3O plus. Okay, so either one in any order. Okay, because they asked for the two conjugate acid-base pairs in reaction 2. So this is as a result of this giving a proton to the base in the reaction, which was H2SO4. Remember, a conjugate base is as a result of the acid donating a proton, and the conjugate acid is as a result of the base accepting a proton. 8.2, a solution of sodium hydroxide, NaOH, is prepared by dissolving 6 grams of solid sodium hydroxide in 500 cubic centimeters of water. This solution reacts completely with 10 grams of impure ammonium chloride, NH4Cl, according to the equation below. Alright, NaOH in aqueous plus NH4Cl solid gives me table salt, which is NaCl aqueous plus, will dissolve the water, plus H2O liquid plus ammonia aqueous. I want us to calculate the concentration of the the sodium hydroxide solution for 4 marks. Alright, let's go ahead and do that. Let's just clear up here quickly. 8.2, let me just get a full screen here. There we go. 8.2. Alright, so the concentration of that, let's use the formula. C is equal to N over V. What will be given in the question? We're given mass and volume. So if we got mass, we're probably going to have to calculate, bring in some molar mass as well. Let's see. Okay, let's use this formula. Just going to transpose it into M over M times big M. Okay, so sodium hydroxide. So sodium, I think it's got 23 plus 16 plus 1. So 23 plus 60 plus 1 gives me 40. Okay, so we'll say C is equal to the mass, which was 6 grams, times the molar mass, which was 40. all over times, sorry, 500 cubic centimeters is 0.5 decimeters. So therefore the concentration, sorry for writing backwards, is 6 divided by 40 times 0.5. That gives us about 0.3 mole per decimeter cubed. Okay, now the other option would be, of course, to calculate the number of moles first in separate formula and then plug it in here. But because all roads lead to the same place, I just use both. Okay, that was 8.2.1. Let's try 8.2.2. Calculate the percentage impurities in ammonium chloride. It's a bit of a longer question. Okay, so let's calculate the mole of sodium hydroxide. We calculated the concentration, but the mole will just be 6 divided by 40. So number of moles is equal to mass over molar mass, which is going to equal 6 grams of the sodium hydroxide divided by 40, which is about 0.15 mole. Okay, let me just double check on my facts. Yes, it is 0.15 moles. Now the ratio, if you just come underneath here, maybe write that in another color, the ratio of sodium hydroxide to NH4Cl, because we have nothing for NH4Cl, so we know that the ratio is 1:1. So that means if we got a ratio of 1:1, that means it's 0.15 moles is to 0.15 moles. So now we can come up here and we can say for 8.2 continued, we can say, well, the number of moles must equal to mass divided by molar mass. So the moles of NH4Cl is also the same, so it's 0.15. We don't know the mass of it though, and we know the molar mass of it. Well, if we get a periodic table here quickly, it's open already here, just at the back of my book. So nitrogen, we got 14 plus 4, because there's 4 hydrogens, and we just add 4 to it, plus 32.5 gives us, sorry, not 32.5, chlorine is 35.5, sorry, 35.5, that's 53.5, so the molar mass is 53.5, and therefore the mass of NH4Cl is equal to 8.025 grams. Alright, that's the mass. Okay, so we got that. We should be cool. Let's see what else do we have here. They say the solution reacts completely with 10 grams impure ammonium chloride. Okay, and what we just calculated was the amount of hydrochloric acid that should be sorry, not hydrochloric acid, sorry, I don't know where I came on that, sorry guys, I think I saw chlorine and then I went straight to HCl, so I do apologize. The amount of ammonium chloride that should be pure is 8.025, and it says impure was 10. So if we take this 8.025 and we divide it by 10 times 100, okay, they ask for percentage impurity, okay, we'll get that to equal to about 80.25% that's pure. So this amount here in mass is pure. So percentage impurities would be to take 100% minus 80.25, that should give you 19.75%. So therefore 19.75% impurities of NH4Cl. NH4Cl. Okay, so we're going to do question 8 again of the 2016 paper, but we're only going to focus on the acid and bases section for this one. The rest are stoichiometry questions, so we're not going to ignore those, but we're just not going to do them for now. We're going to ignore the first question, define an acid in terms of Lowry-Bronsted theory. I think we can all do that. 8.2.1 though, when we consider the following acid-base reaction, they ask us to give the conjugate acid-base pairs in the above reaction. Okay, so we can do that though. So let's just write down the reaction. I think we got hold on, I can't remember it, sorry. H2PO4 minus, minus plus, what was the base there? NH3, and that gave us HPO4 2 minus plus NH4 plus. Am I right? Yes. And the conjugate acid base pairs of the above reaction should look as follows. Okay, so HPO4 2 minus add H2 PO4 minus. Of course, a proton goes from the acid here to the base, which is ammonia. So here we have the conjugate. From the acid, we have the conjugate base, which forms as an acid. The substance that is as a result of the, sorry, this one is here, HPO42 minus, is the substance of this. This is the acid. Okay, so this would be your A1, and I think this would be your B1. This would be your B1, yes. And because this is the substance that forms after the acid gave up a proton. So this is the conjugate base. Okay, and then we've got the conjugate acid over here as a result of the ammonia accepting a proton. So we have a conjugate acid of a base, NH4 plus. So those are the pairs. Okay, those are the pairs. And then 8.2.3, we skipped out 8.2.2, define the term ampholyte. We know what an ampholyte is, substance that can act as an acid or a base. The 8.2.3 says choose an ampholyte in the reaction. So in other words, an acid or a base, it can either accept or donate a proton. So in the above reaction that we have here, H2PO4, we see it's still got another 2 protons or hydrogen protons to donate. So it's still H2PO4 minus, can act as an acid or base. It can act, because of this over here, shows that it can still accept a proton, but because of this over here, shows that it can still donate more protons, 2 to be exact. There's another substance which is also HPO4 2 minus. This is also an ampholyte. This over here shows that it can still donate a proton, but also accept another 2 protons. This over here also shows that it can donate 1 more proton. Also, it can accept another proton as well. So, there are 2 ampholytes. You can choose either one. Doesn't really matter which one you choose. They are both ampholytes in terms they can either act as an acid and donate, or they can act as a base and accept. And that's where we'll leave things for tonight. Grade 11s, thank you so much for joining me in this tutorial on the basics of acid and bases, the conjugate pairs, and answering a few exam questions. Okay, we're going to leave it there for this evening for this tutorial. We will come back to acids and bases when we have a look at titration calculations. That'll be a little bit at a later stage on in this here. Okay, don't forget to like this video as well as comment on it and subscribe to our channel, Good Better Best Online Videos. We'll see you in the next one.